Hello, everybody. I'm Zifeng Wang, a PhD student from Northeastern University.
My name is Tong, a PhD student from Northeastern University as well.
Yeah, so today we're going to talk about our paper, Learn-Prune-Share for Lifelong Learning. So let me do the first part first. So human beings have a natural ability to adapt to different tasks sequentially without forgetting what they have learned. This is called lifelong learning. Humans can also seamlessly leverage knowledge learned from past tasks to tackle new tasks. Also, we want our machine learning models to have this property as well, to continually learn the sequence of tasks, just like humans. In concrete terms, in a lifelong learning setting for machine learning models who wish to maintain and update a model, for example, a neural network classifier, in the presence of new classification tasks that arise sequentially. The model should both exhibit high accuracy on new tasks as well as performing well on old classification tasks, even if the old data is no longer available in the future. So in our paper, we mainly focus on supervised lifelong learning, where a multi-head model is applied for the sequence of tasks. So the multi-head model, as its name suggests, has one common feature extractor, FW, shared among all tasks, and different fully connected layers as output layers for each task specifically. So here are several challenges of supervised lifelong learning called parsimony, preventing catastrophic forgetting, and achieving knowledge reuse. So first of all, we want to maintain a single model instead of training a model for each emerging task. Having a parsimonious model is of great practical meaning, especially when the storage and computational power is limited. And secondly, catastrophic forgetting refers to the phenomenon that, especially for a neural network, classifiers trained sequentially on different tasks may forget how to deal with old tasks, meaning that the performance on old tasks may decrease a lot when trained on new tasks. Lastly, based on parsimony and solving the catastrophic forgetting problem, we want to achieve knowledge reuse. Some features learned from old tasks may be helpful for new tasks. So we really need a systematic way to find out which knowledge are useful for future tasks. There are already some prior work on lifelong learning, so they mainly try to attack these challenges explicitly or implicitly. So most of the prior work could be classified into 3 categories. However, each of the categories has its own limitation. For regularization-based method, the performance on previous tasks gets worse when more and more diverse tasks are seen. For the rehearsal-based method, the model needs additional cost of training and storing an external generative model for generating old tasks. And for the final one, the expansion-based model, the size of the model parameters grows linearly with the number of tasks. So in our paper, we proposed a new lifelong learning method called Learn-Prune-Share, try to tackle the 3 challenges together. So our contribution is as follows. We proposed an ADMM-based pruning strategy with novel knowledge sharing scheme, and there's no catastrophic forgetting in our model. And we improved the state-of-the-art methods by a margin from 2% to 54%. Here's the outline today. I'm going to introduce the Learn-Prune-Share algorithm, and then followed by some experimental results. And finally, I'll conclude the presentation with conclusion and future work. So first of all, in this section, Tong and I will introduce the Learn-Prune-Share or LPS algorithm. Let me start with a simple but intuitive example. We visualize the weights of our neural network classifier as grids. The blank squares represents the initialized but untrained weights W, and the shadowed square represents fixed weights, which will be used later. We use color red to represent task 1, And the first step we do is kind of trivial. We just train the whole neural network for task 1 so that the whole capacity is used for this task. However, we really don't want task 1 to take up all the capacity of the neural network. So we do something different. We adopt the pruning strategy, which will be illustrated later, to compress the whole neural network so that only part of the weights, say here, you can see that in the figure, only part of the weights are marked as red. So this part of weights are used for task 1. Other weights are set to 0 so that they could be used for future tasks. So in the figure, we can see the red weights as W1, and we call this step prune. And that is all for task 1. So for the second task, task 2, we basically repeat the same learning process. However, in order to not interfere with the previous performance on task 1, we fix the part of W1, which is specifically reserved for task 1. So that is why there is no catastrophic forgetting, because we kind of fix the weights for task 1. So we do the prune process again. In this sense, we get the task-specific weights W2 that is used for prediction for task 2. However, there's also something different from what we have done in task 1. So for task 2, we already have some prior knowledge learned from task 1. So in order to share some useful knowledge learned from all tasks, we designed a knowledge sharing mask, here M2, to just borrow some parts from W1. So note that M2 is a binary matrix so that we can achieve weight sharing by performing element-wise multiplication between M2 and W1. So here, formally speaking, for task 2, we use both task-specific weights and knowledge sharing mask to make the prediction. So the dot product, the dot product here means the element-wise multiplication. And we repeat this process again and again till the very last task, task n. So look at the figure. For every task, except the first one, we have a corresponding task-specific weights and knowledge sharing mask. So just to sum up, our Learn-Prune-Share algorithm maintains a single neural network for the sequence of tasks, while we're doing 3 things together simultaneously. We're learning the tasks, and we're pruning the neural network so that each task just uses up a small portion of the capacity of the neural network. And finally, we're sharing knowledge among tasks, use the knowledge sharing mask specifically for each task, without influence the previously learned weights for all tasks. So in the end, we will have a full model with weights and a mask to describe capacity used for each task. So this is all for my part, and Tong will illustrate the details of LPS in the next part. Thank you.
Thank you, Zifeng. I will take over for the rest. Formally, we have this objective function to describe our RPS algorithm. Again, W is task-specific weights we want to learn. M is knowledge sharing mask. W bar represents the sum of the task-specific weights. Here, W bar T minus 1 represents the combination of the weights until task T minus 1. This objective function describes our algorithm, tries to find the best task-specific knowledge, WT, as well as many of the previous task weights, W bar T minus 1, that we wish to leverage. This function has several constraints. The first one enforces sparsity for task-specific weights. No matter convolutional layer or fully connected layers, weights could be represented as a 2D matrix with size of P times Q. Alpha T here is the pruning ratio, which is a constant limiting the proportion of non-zero elements. So the constraint set SLT here implies that the weights has no more than alpha t number of non-zero elements for task T. The second constraint infers sparsity on knowledge sharing mask. Similarly, sharing parameter beta limits the proportion of old weights to be shared weights. For example, beta is 90%, means we use 90% of the previous weights. This conveys the usefulness of previous knowledge. When tasks are similar, we may want beta to be larger. And for dissimilar tasks, we expect this value to be smaller. We will see this phenomenon in experiments later. The third constraint enforces task-specific weights are disjoint, so that each task can occupy and leverage its own weights. And the first one enforces that knowledge sharing masks are applied to the past weights only. This optimization is over non-convex constraint sets, so that it cannot be solved by stochastic gradient descent. In practice, we solved it by ADMM. ADMM is the short of alternating direction method of multipliers. By leveraging ADMM, the optimization over non-convex constraint sets reduced to orthogonal projections and still staying in continuous domain, making the problem easily be solved in polynomial time. All right, let's take a look how our LPS algorithm performs in practice. We evaluate LPS algorithm on 3 datasets: 2 standard lifelong learning benchmark datasets, permuted and mixed, and split cipher, and also a real-world dataset we call it split reef. We implement different architectures for these 3 datasets, as suggested by their original authors, respectively. And this architecture worked as the feature map FW, as you can see on the red plot. Let's first look at LPS performance on cipher dataset. We compare our LPS algorithm to 6 competing methods on the final per task accuracy and also the average accuracy over all the tasks. Our LPS algorithm performs best. And among all, LWF, which is one of the regularization-based method, has the significant forgetting issue. Accuracy of the previous tasks decreases a lot comparing to the later tasks. While pruning-based approach, PACnet, and our LPS algorithm are immune to forget. Among all the methods, PACnet is the most similar one to us. It compresses the original model to allocate free capacity for new tasks, but it only uses simple threshold technique to prune the model and consider tasks independently. So that's why we observe LPS performs better than PACnet. SM is training a full capacity single model separately for each task. We can see that LPS even outperforms SM, indicating that LPS avoids overfitting. Also, we see prediction on later tasks improves under LPS compared to SM. This is a clear benefit of reuse of parameters across tasks. We also reported the final averaged accuracy across all tasks for 3 benchmark datasets. Again, our LPS algorithm performs stable and reaches a high level accuracy on 3 datasets. Besides this, another observation here is regularization-based methods, such like EWC and NS, perform relatively well on benchmark datasets, while they fail on split RF. Split RF is a pretty hard dataset. The tasks are more diverse and the model is large. So the regularization-based method may not have the ability to keep the learned information very well. So, okay, before exploring more, a natural question could be asked. What happens if we just use a portion of the model? Does our method have the ability to scale up? To answer this question, instead of using the whole model capacity, we use only a fraction of the full model. So the figure here shows the impact on average as well as per task accuracy when we vary this fraction. For example, 10% of the model capacity usage on the x-axis means we use only 10% of the full model capacity to learn all the tasks. We can observe that a model performs better when more capacity is available. Nevertheless, accuracy performance is also robust to this shrinkage. We can still get 75% by using just a 50% capacity. It degrades less than 5%, which is even better than the best non-pruning method AS with full model capacity. This indicates that our method has the potential capacity to scale to even more future tasks. We also explore the impact of knowledge sharing. We alter the sharing ratio and check its influence on the performance. Here on the plot, 15% share on the x-axis means we use 50% weights from the previous tasks. We can observe that the optimal value is at 92%. This also indicates that many past weights are meaningful for the new task, but not all are valuable. To further explore the share effect, we've conducted a dataset in which tasks vary a lot by replacing 2 safer datasets with 2 administered datasets. The model performance is quite different. The highest accuracy is achieved by 20% share. This demonstrates that LPS algorithm does adaptively select useful knowledge for the current task. When tasks are not similar, it prefers to use less weights. Okay, as a conclusion, in this work, we propose LPS Learn-Prune-Share algorithm for lifelong learning. Our method maintains a single neural network model and achieves exact no forgetting by splitting the neural network into task-specific partitions using ADMM-based pruning method. And our method can address a knowledge reuse issue by a selective knowledge sharing scheme. Some future directions could be we can apply more advanced pruning strategies on the lifelong learning problem. And also we can explore how to measure the capacity of a model. Also, sharing ratio is a hyperparameter needs to be defined right now. We may need a more flexible algorithm to adaptively decide this sharing ratio based on task similarity. Thanks for listening. If you found this topic is interesting, please feel free to visit our session. We will be glad to see you here.